Hi everybody. In this lecture today, we're going to talk about the origin and the composition of soils. Soils typically contain the same components such as gravel, sand, silt, and clay. Then why we need to know the origin of soil? Although soils typically consist of the same components, they usually have different structures, which are generally relevant to soil origin. As different soil structures give rise to different soil properties, the knowledge of soil origin can provide us with important information about what geotechnical problems we may have to deal with. Soil grains that form the solid phase of a soil mass are the product of rock weathering, and their size changes greatly. As the physical properties of soil are dominated by the size, shape, and chemical composition of the particles, one must be familiar with the basic types of rocks. Rocks can be categorized into three basic types based on their mode of origin. They are igneous, sedimentary, and metamorphic rocks. In the figure here, you see the formation cycle of different types of rock and the processes related with them. This is called rock cycle. Now, let us briefly look at three basic types of rocks. Igneous rocks are formed by the cooling and the solidification of molten magma ejected from deep within the Earth's mantle. Depending on the proportions of minerals present, different types of igneous rock are generated. Granite, gabbro, and basalt are some of the common types of igneous rock generally met in the field. The deposits of gravel, sand, silt, and clay formed by weathering may become compacted by overburden pressure and cemented by agents such as iron oxide, calcite, dolomite, and quartz, generally transmitted in solution by groundwater. Limestone, gypsum, conglomerate, mudstone, sandstone, and shale are some of the sedimentary rocks. Metamorphism is the process of changing the composition and the structure of rocks by means of heat and pressure. During this process, new minerals are generated, and mineral grains are sheared to give a foliated texture to metamorphic rock, as seen in the figure. Quartzite, marble, schist, gneiss, and phyllite are types of the sedimentary rocks. All soils come from the weathering and/or disintegration of rock themselves. Dissimilar to rocks, soil contains much smaller sized material forming two main groups, namely coarse-grained soil such as gravel and sand, and fine-grained soils like silt and clay. There are two types of weathering: mechanical, in other words, physical, and chemical. Mechanical weathering is the breakdown of rocks into smaller particles. The main agents in mechanical weathering are freezing and thawing, glacier ice, heating and cooling, wind, running water, and ocean waves. In the freezing and thawing process, water penetrates into pores and or cracks of rock masses. As the temperature drops, water freezes and expands. The pressure exerted in this way is sufficient to break even the large rock masses into small pieces. Do you know that even plants and animals can be agents of mechanical weathering? While the roots grow, they exert pressure and widen the cracks, eventually breaking the rocks into small pieces. In chemical weathering, the original rock minerals are converted into new ones by chemical reaction. The main agents in this process are water, carbon dioxide, oxygen, and decayed organic matter. Water and carbon dioxide from the atmosphere generate carbonic acid, which in turn reacts with the existing rock minerals to form new ones, and soluble salts. Soluble salts available in the groundwater and organic acids resulted from the decayed organic matter also result in chemical weathering. If the products of weathering stay at their original location, they form a residual soil. The residual soil is predominantly firm and only moist, which makes it better foundation for construction. However, if the products are carried and collected in a different location, they form a transported soil. Contrary to residual soil, this soil type can potentially lead to lots of trouble because of its unfavorable properties. The transported soils may be classified into several groups depending on their mode of transportation and deposition. Glacial soils formed by transportation and accumulation of glaciers. This type of soil is typically of high strength and it generally provides a high bearing capacity for engineering structures. Alluvial soils, on the other hand, transported by running water and collected along streams. They are typically soft and loose material saturated with water. Many geotechnical problems, including liquefaction and large settlements of engineering structures, take place in alluvial soil. Lacustrine soils formed by deposition in quiet lakes and have similar properties as marine soils. This type is not widely spread because it is limited to the area of lakes and swamps. Marine soils, constituted by deposition in the seas. This type of soil tends to be rather soft and saturated. It is mostly fine-grained material such as silt and clay. Similar to alluvial material, marine soils can experience significant settlements under stresses. Aeolian soils, transported and collected by wind. It is typically of yellow color and made of fine particles, mostly silt. Although this soil can be very hard when dry, it may quickly collapse when it gets saturated. Collivial soils, formed by the movement of soil from its original place by gravity, such as during landslides. It is a loose deposit and not consolidated and has low shear strength. What about the topsoil, the soil found on the ground surface? It is organic in nature. Is it important? The end product of plant and animal remains are known as humus, which generally forms the upper 50 centimeter thickness of ground surface and has unfavorable properties such as low strength, high compressibility, and low bearing capacity. When rocks go through weathering process, their mineral composition will change. That is to say, rock minerals turn into secondary or clay minerals. There are a few common clay minerals, such as kaolinite, illite, and montmorillonite, that play an important role in soil behavior, since they determine the properties such as plasticity, permeability, compressibility, and strength. Soils with smectite or montmorillonite frequently induce problems during construction because of the fact that such soils can absorb and hold lots of water, which would make them soft and weak. Is it then necessary for each project to determine the clay mineralogy? It is recommended, but not a must. It is not very common for small to medium scale projects where more attention is paid to soil properties like grain size distribution, plasticity, and strength, which are utilized for design purposes. Furthermore, special equipment is required to perform X-ray tests on soil, which make it relatively expensive. Clay minerals are complex aluminum silicates comprised of two basic units, namely silica tetrahedrons and alumina octahedrons, which are symbolically represented in the figures as silica sheet and alumina sheet. Kaolinite contains combined silica alumina sheet held together fairly tightly by hydrogen bonding, as you see in the figure here. Water cannot easily penetrate between combined sheets. For that reason, it is less sensitive to volumetric change, such as swelling and shrinkage. The figure on the right displays a scanning electron micrograph of a kaolinite specimen. Illite is made up of an alumina sheet bonded to two silica sheets, as shown in the figure, one at the top and another at the bottom, and the sheets are combined together by fairly weak bonding due to potassium ions. Compared with kaolinite, illite is more sensitive to shrinkage and swelling, and the figure here illustrates the fabric of illite by way of a scanning electron micrograph. Montmorillonite consists of the same basic structure as illite, but there are water molecules and exchangeable cations other than potassium in between combined sheets. Bonding is very weak due to these ions. Thus, considerable swelling can take place owing to the additional water being adsorbed between the combined sheets. The scanning electron micrograph on the right-hand side shows the fabric of montmorillonite. Other clay minerals generally encountered are chloride, halloysite, vermiculite, and attapulgite. The important properties of clay minerals are as follows. The smaller and more flaky a particle is, the greater will be its surface area. The ratio of surface area per grams of mass is described the specific surface area. Specific surface area of some clay minerals are presented in the table here. As you notice, montmorillonite has the greatest surface area. It is interesting that 6 grams of montmorillonite has an approximately the same surface area as an entire football field. The second important property is the surface charge and adsorption. Faces of clay particles carry a net negative charge resulting from isomorph substitution and a break in the continuity of the structure at its edges. Actually, edges of the clay particles are positively charged. Water molecules are dipolar, which means a water molecule has a positive charge at one side and a negative charge at the other side. This is known as dipole. So dipolar water is attracted both by negatively charged clay surface and cations in solution. Cations in turn attract water molecules. So a layer of water held tightly very close to the clay surface is known as adsorbed water. The properties of adsorbed water are different from those of free water. For example, it is more viscous than free water. As the distance increases from the clay surface, the attraction force between clay particle and water molecule decreases. So, water beyond boundaries behaves randomly. This orientation of water around the clay particles causes clay soils to gain their plastic property. The third important property of clay minerals is the cation exchange capacity. It is defined as the amount of exchangeable ions expressed in milliequivalents per 100 grams of dry soil. The cation exchange capacities of kaolinite, halloysite, illite, montmorillonite as milliequivalent per 100 grams are 5, 15, 30, and 100 respectively. Flocculation and dispersion is the fourth property of clay minerals. When the adsorbed layer is thin, owing to base exchange process, the attraction will be greater, and the orientation of particles tend to be edge to face or edge to edge, which is referred to as flocculated structure. Clay deposits set in the sea are highly flocculent. On the other hand, When the adsorbed layer is thick, the repulsion will be greater and the particles tend to assume a phase-to-phase orientation. This arrangement is referred to as a dispersed structure. In this case, all particles are oriented more or less parallel to each other, as illustrated in the figure here. Most of the sediment deposits formed from fresh water have an intermediate structure between dispersed and flocculent. Does the structure make any difference from engineering point of view? Yes, it does. Soils having a flocculent structure have higher strength than those of dispersed one, but lower compressibility and higher permeability at the same void ratio. It should be kept in mind that the presence of clay minerals in a soil aggregate has a great effect on the engineering properties of soil entirely. When moisture is available, the engineering behavior of a soil will change greatly as the percentage of clay mineral content increases. For all practical aims, when the clay content is about 50% or more than that, the sand and silt, even gravel particles float in a clay matrix, and the clay minerals primarily dominate the engineering properties of soil. A deposit of pure clay minerals is unlikely in nature. When a soil has 50% or more particles with sizes of 2 micron or less, it is generally termed clay. Although it is termed clay, the proper name should be clayey soil. Now then, shall we recap what we have learned so far with a review quiz? All you do is to mark the right answer for the coming up multiple choice questions. The first one, what are the two weathering processes? Yes, it is B, physical and chemical. The next question, which statement is incorrect? No, it has to be C. Volcanic rocks are more resistant to weathering than other types of rocks. Which soil is mostly associated with collapsibility? No, it is not. The right answer is aeolian. And the next one, what type of soil is formed by deposition in lakes? Congratulations. The right answer is lacustrine. And the next question, which one of the following is not a clay mineral? No, I'm sorry. The right answer is D, feldspar. Alluvial soils are transported by, yes, you are right, it is B. Good. Expansive soils swell because they contain an abundance of, no, it is not. It is, the right answer is Mount Morillonite. What causes clay soils to gain plasticity? Yes, you got it. The right answer is B, diffuse double layer of water. What type of soil would generally have more favorable geotechnical characteristics? Yes, you are right. The answer is alluvium. The next question is, which one of the following is not a sedimentary rock? No, no, the answer is gabbro. And finally, which one of the following is not correct? Yes, you got it. The answer is C. Soils having a flocculent structure have higher compressibility. Well done. So we have come to the end of our lecture. Thank you for your attention. Hope to meet you again. Have a nice day.